Hi, this is Dane Quinn from the University of Akron. Today, I'd like to give you a fairly detailed lecture on modeling. This material has been in bits and pieces in a lot of the previous lectures that we've dealt with, right? But I've tried to really take everything and combine it together into one general lecture about what kinds of questions to ask, how to proceed in general when you're modeling systems. So let's go ahead and start this. Really what we're talking about is dynamics, right? So it's the application of the laws of mechanics. And ultimately, what we want to do is develop equations of motion to describe the response of a system. Now, when we talk about dynamics, we break that up into two different parts. One part is kinematics, right? So kinematics is sort of what could happen. It's a description of the allowable motion of an object. So it takes into account the constraints that act on that object, but what it doesn't take into account is what causes that motion. So really, kinematics, just think about it as what could happen, or the allowable motion of a system. Then kinetics is the second part of that, and that's a description of the forces and the moments that are applied to a mechanical system. So what kinds of effects cause that motion? Then dynamics puts all those together through the laws of mechanics. So here we have a particle P. It's got some mass. It is a point mass, and it's moving with some velocity, shown here, v of p. And then we assume that there's a force that's applied to this particle, right? So F. What happens? What's the motion? That's going to be determined by linear momentum balance, or sum of the forces that act on this object, here that I've only shown one, is equal to the mass of the object times the acceleration of the particle, right? Again, it's a point mass. And this is linear momentum balance. And it's valid for any particle, right, or any small bit of mass. Now, when I look at this equation in terms of what we've discussed before, then this whole thing is dynamics. Right? Dynamics is about coming up with this equation. If I think about these two parts, well, the allowable motion, that really describes the acceleration, right? What could happen. So the right-hand side is the kinematics. And then the left-hand side is the kinetics, right? So a description of the forces. Again, we take the forces that act on a system, we take what could happen, and we put that together using momentum balance to develop our dynamical equations. So now this is for a particle, right? We have linear momentum balance. But we're going to be concerned with larger objects, rigid bodies, in fact. And so rigid objects can translate, and that's best described as the average velocity of this body. And they can rotate. So different points on this object can move in different directions, right? So there's a relative velocity between, say, a point over here on the right and maybe a point over here down on the left. So this idea of translation and rotation can be described by the general equations of momentum balance. In particular, the motion of the mass center, right? So the mass center is this special point that's sort of at the mass averaged location of the body. The motion of the mass center is described by linear momentum balance. So essentially, the mass center behaves like a particle. But then we have all this relative motion of points that are distributed throughout the body. And the rotation is then determined from angular momentum balance. Angular momentum balance is written as the sum of the moments about the mass center is equal to the moment of inertia of the object about the mass center times the angular acceleration of the body. And again, thinking about these categories above, right? This whole thing is dynamics. The kinematics is worried about what could happen, right? So what kinds of angular accelerations are possible. And then the kinetics is about what forces or moments are applied to the object. So in general, these are the equations that we use: linear momentum balance, and for objects, right, it's going to be linear momentum balance written in terms of the mass center, and then angular momentum balance to describe the resulting rotation of the object. Now, what about a solution procedure? Well, so in the time that I've been doing this, right, this is the framework that I have developed. And to describe this, I'm going to actually start at the end. So if I want the equations of motion, I have to apply momentum balance, right? So the last thing I'm going to do is take the sum of the forces and set that equal to the mass times acceleration, and the sum of the moments and set it equal to I alpha. And I should note that this form of angular momentum balance is valid for planar motion. But again, the last thing I'm going to do is apply the laws of mechanics, right? Because that's where I get the equations of motion from. When I talk about problem-solving procedures, well, I need to get myself to the point that I can do this. What's involved in that? Well, the thing that I'm going to do right before is describe the forces, right? So I'm going to draw a free body diagram, and I'm going to properly label all the forces. And that's going to go right here in the right-hand side of each of these equations. So the second to the last thing I'm going to do is describe the kinetics. Now, what am I going to do before that? Well, I'm going to describe the allowable motion, right? I need a description of what could possibly happen. And so I'll identify the accelerations of all the objects, including rotational acceleration, as well as any constraints in the motion that's provided by the structure of the system. And so now I'm 2 steps back. Arguably, these 2 steps are kind of at the same level, right? I have to choose one to do first. So I always choose to do the kinematics first, and then I do the kinetics through the free body diagram. You could switch the order here, but this is the procedure that I use. Right, so now, what does it take for me to describe the free body diagram and the kinematics of the system? Well, in order to do that, I need some coordinates and directions. I need to know how I'm going to measure the motion. I need to know what directions are important. I need to know what directions the forces are in. I need to know, if I have a spring force, what does that force depend on? So before I can do either one of these things, right, I have to identify some coordinates and directions. So we'll draw arrows from here to here. Knowing these coordinates and directions, right, I can go forward and describe the kinematics, which ultimately comes into the right-hand side. Knowing these coordinates and directions, I can describe the forces, which then comes into the left-hand side, moments as well. Well, now the question is, what do I need to do in order to describe the coordinates and directions? Well, really, I just need to think about what's going on. I need to look at the problem that I have, and I need to identify the objects, right? I need to describe what forces are there. I don't actually need to write those forces down, but I need to know that they're acting on the different objects. I also need an idea of what's going to happen in terms of the motion, right? So really, this step is just thinking about the problem. There are a couple things I'll do here, right? But really what I want to do is identify the objects and the forces, together with the possible configurations. Again, we have this allowable motion kind of concept. And this is it. So when you are solving for equations of motion, when you're modeling a system, this is the procedure that you go through, right? And I developed this by working backwards. But going forwards now, this is where we start. The first thing you should do is identify the objects, identify the forces, right? Think about the motion of the system. As part of that, we'll look at the degree of freedom, right? But that's always where you start. Don't try to jump right to the end. Don't even try to jump to free body diagrams or the kinematics without going through these steps. And if you can get in the habit, if you can make this your solution framework, you'll be able to solve any problem that you're given. Every single problem that we have done to date, and every single problem that we'll do in the rest of this course, follows this procedure. Identify the objects, forces in motion, which will tell you what coordinates and directions that you should define. And then using those coordinates and directions, we'll describe the allowable motion. Kinematics, we'll describe the forces through our free body diagram. And then finally, we'll put that stuff together with the laws of mechanics to develop the equations of motion. Okay, so now let's go through this with an example. I'm going to take a disk of mass m and radius r. That's shown here in this dark gray that is rolling without slip on the surface. Now, then I have an outer hub that has radius 2r that is rigidly attached to that inner hub. So think about like a spool, maybe, with an inner hub and an outer hub. The inside of the hub now is rolling on the ground. And that outer portion has a cable wrapped around it that then supports a block of mass m. We have gravity in this problem, and that block is then hanging down. Finally, we have a spring and a damper that are connected to the center of the disk. So what I want to do is find the equations of motion for this system in terms of the displacement of the block. And I'll find a couple of other things as well. So where do we start? Well, we know where to start. We start by identifying the objects and the forces and the motion. So let's do that on the next page. Now, what you're going to see in this video lecture is these broad categories. Identify objects, forces, and motion, for example. And then you're going to see some questions and some things that you want to do as you're carrying out this step. So in particular, the first thing I always ask is, well, what are the objects? Here, the objects are going to be the block, right? And I've kind of redrawn those down here on the left. Well, the block is certainly one object. I'm going to apply linear momentum balance to that. Then I have this pulley. It's massless, but it's still important. There are forces that act on this, and I need to relate, right, the force hanging down to the force that then connects to the disk through that cable. Finally, my third object is going to be the disk itself, right? I have the inner hub, I have that massless outer hub, and momentum balance can be applied to every single one of these. I mean, in general, you can apply momentum balance to anything. It's a law of nature. It has to hold. Not just some places, but it has to hold everywhere. So if you're ever in doubt about should I apply momentum balance to this object, the answer is yes, right? Because you can, and it's always going to be valid. Now, we'll ask, how do these objects move? Right? What are the possible configurations of the system? Well, this disk rolls without slip, right? So this inner hub, essentially it rolls back to the left, back to the right. It'll roll back and forth on this surface. That outer hub is rigidly connected, right? So as the inner hub rolls, the outer hub moves as well. The cable is wrapped around that outer hub. So for example, as this disk rolls to the right, that cable is going to pull the block up. As it moves to the left, the block will go down. So we see that these things are all connected. And now we want to identify the forces and moments that act on these objects. I don't need to know what they are. I just want to know that they're there. What forces act on the block? Well, we're going to have the weight. Right, so that's going to be, say, W of B, the weight of the block. We'll also have the tension from the cable. We'll assume that's directed as T1. Now, if I cut this cable, I have forces that act on the pulley that have equal magnitude and opposite direction. So the force acting on the left side of the pulley is going to be minus T1. Then I'm going to have a reaction force from the cable connecting the pulley and the disc. That's going to be T2. And finally, I could have a reaction force at the center of the pulley, right? I mean, something's got to keep this thing pinned to the ground, right? And that's going to be this reaction force that constrains the motion of the pulley. Now, one thing I want to note is that T1 is the force acting on the block, and minus T1 is the force acting on the pulley. Again, because I cut this cable, right, to identify these forces are internal, right? So internal forces must balance out. Right, so whenever I make a cut, on one side of the cut, I have a force. On the other side of the cut, I have the opposite force. Right, so again, when I add these two together, equals 0. Notice that I haven't cut the pin away, right? So there's just a reaction force. Now, if I wanted to consider the ground, I would then have a equal and opposite force acting on the ground as well. But notice that I do have one more internal force on this system. So when I cut this upper part of the cable, right, and identify the force T2, well, the force acting on the disk is the negative of that. So that's minus T2. All right. What other forces act on this disk? Well, I have the weight, right? So we'll call that W of D, D for disk. At the contact point here, I have a contact force, and I'm going to break that up into a normal component, say N, and a component due to friction, Fr. You may look at this and say to yourself, well, the normal force is going to be equal to the weight. And I would not dispute that, right? In fact, I'd agree with you. However, I don't want you to make that assumption. I want the laws of mechanics at the very end to show you that that's true. Those kinds of decisions are best left to, again, the laws of mechanics. And what about this friction force? Well, we know friction has, coefficient of friction and those kinds of things. But here, because I'm assuming that the disk does not slip, all I know is the friction force is less than mu n. I don't actually know what it is, right? So this is an unknown value. I just have to leave it as some force in the horizontal direction. Now, the last thing we have is the force due to the spring and the damper. These act together, right? So I'm going to write this as Fs plus Fd, the spring force and the damping force. Acting, again, they act at the same spot, so we'll just add them together. Now, you may look at this and ask about the directions of these forces. And my answer is, right now, they don't matter. I haven't even defined a direction yet. All I'm trying to do is identify that these forces are here. So when it does come time to consider the forces in a free body diagram, I just know that I'm not missing anything. Again, you don't have to get any kind of directions right. The arrows don't matter. They don't matter at all. The only thing that matters here is that I'm accounting for the various forces that act on the various objects. Now, let's determine the degree of freedom of the system. This is going to be an important thing for us to know because the degree of freedom is equal to the number of second-order equations that we're going to have. So knowing the degree of freedom of a system can tell us a little bit about what to expect, right? So it's a good thing to calculate at the beginning. Here, the motion of the block, again, up and down, is then tied to the motion of the top of the disk. And that is then tied to the rotation and the displacement of the disk, right? So in fact, this is a single degree of freedom system. If I know any of those measurements, I can figure out where the rest of the system is. I can determine the configuration. So I only need one measurement here to specify where absolutely everything is in this system. Therefore, it's a single degree of freedom system. That's what it means when we talk about degree of freedom. It's how many independent measurements do I need to specify the configuration. Ultimately, this will have a form that looks like our spring mass damper system, right? Because all single degree of freedom systems with constant coefficients are equivalent to that system, right? So we kind of know what we're going to look for at the very end because we just calculated the degree of freedom. Okay, so what's next? Here's our framework, right? Here's our flow chart. So now that we've identified the object's forces in motion, we want to go and define the coordinates and directions, right? So in particular, we want to identify the directions that are associated with the forces and the motion. And then we want coordinates that will allow us to describe both, right? To use within the kinematics as well as the kinetics, or the forces and the moments. So again, here's our step that we're at, and these are kinds of the things that you want to do. You want to start off and identify all the directions. So what directions are important for this problem? Well, the block moves up and down, right? So up and down is going to be an important direction. And the displacement of the center of the disk is left and right. Well, those two form a set of bases, I and j. And then, of course, we're using a right-handed coordinate system, so k comes out of the board. And for this problem, quite honestly, these are all the directions that I'll need, right? There's no inclined plane, there's nothing that's rotating, there's no bars, right? So I, j, k, that's a good set of directions. It naturally describes the motion of the objects as well as all of these forces. In fact, the only force that's not in either the I or the j direction specifically is this reaction force on the pulley. And we can always break that into components in the I and j direction if we need to. What coordinates do we define? I usually start with the kinematics because I know that I'm going to need coordinates to describe the motion. So how can we measure the motion of this object? Well, let's see. Let's think about the rotation of the disk first. I can measure the rotation with an angle theta. Right? So theta, again, measures the rotation of the disk, right? That's going to be used when we talk about angular momentum balance. The center of the disk moves back and forth, right? And so let's say the center of the disk is G, and again, that moves back and forth. Let's measure the displacement of the mass center. Now, rather than drawing a coordinate to this point, I'm going to identify a point that's just over here, and I'm going to define the displacement, or I'm going to measure the displacement of that point. Right? So let's call that y. Y slightly to the left. Well, it just makes it a little easier to see. In particular, we'll see that when we start talking about displacements of different points over here. But the displacement of this point and the displacement of the center are exactly the same. In fact, every point on this cable, all the way back to the spring and the damper, right, have the same displacement, right? So they'll all displace by a value of y. And I'll remind you that all coordinates are going to be measured from a common configuration so that they all vanish simultaneously. So if theta is equal to 0, y is equal to 0. Now, what about the block? All right, well, the block moves around, so let's measure the displacement of the block. And again, I'm going to identify a point that's on this part of the cable, and I will define that displacement as x. Right, so let's say this is point B, B for block. So the displacement of the block is x. The displacement of the center of the disk is y. The rotation of the disk is theta. And now we need to tie these things together. So let's actually go and measure the displacement of a point on the upper cable. We'll call that W. And identifying this point at the top of the disk, we'll say that's A. Finally, we will need to identify the contact point, and we'll call that C. So here we have coordinates for all the kinematics. This describes the motion of the block, the motion of the mass center of the disk, and the rotation of the disk, as well as this point up on top of the disk that's ultimately connected to the cable. So we have x of t as the displacement of the block, and in particular point B. Y of t measures the displacement of the disk center through the point G. we have theta, which is the rotation of the disk. And then finally, W, which really measures the displacement of the point on the cable at the top of the disk. So this is the cable connecting the block to the disk. And that's going to be related to what's going on here at A. Now, we need to define coordinates for the forces. We need coordinates when forces are related to the configuration, and those are in particular springs and dampers. Notice that none of these forces, with the exception of Fs and Fd, are from springs or dampers, right? So these will all be defined in terms of just some maybe known magnitudes and known directions, as in the case of W, maybe unknown magnitude in terms of the friction force or the tensions. But springs and dampers are very special because they are related to the displacement. If I know where this center of the disk is, then I can tell you what the spring force is. I don't know what y is at this point in time, right? But if I knew y, I could tell you what the force is. Likewise, if I know y dot, I can tell you what the force in this damper is. Right? So the force Fs and Fd depend on the configuration. So they need a coordinate so that we can measure the right configuration, or at least the right thing about the configuration. But you know what? Fortunately, we have that. We have y. Y is related to the force in the spring and the force in this damper. So in this problem, I actually don't need an additional coordinate. I've already got one that does the job, because y was also important for the motion of the center of the disk. Right? So I don't need to go and identify a separate coordinate for the spring and the damper. But I do need to make sure that I have a coordinate that describes the force in the spring and the damper. And y serves both purposes. Okay, so awesome, right? I have coordinates that I can use, right? I've got the directions defined. Let's go on. In our flowchart, what comes next? Well, kinematics. That's kind of step 2, right? I don't really call this a step number, right? Because all we're doing really is just kind of thinking about what's going on. Coordinates and directions is where we first really get involved, right? So this is now step 2. We want to express the kinematics, or the allowable motion, in terms of those coordinates and directions that I just talked about. Here they are again. These are all the coordinates. These are the directions. So I want to define the motion in terms of these coordinates and directions. And I want to do so that I can apply the equations of motion. Well, that means that I need the linear and angular acceleration for each object. All right, so let's think about the block first. Well, the block actually doesn't rotate, so I don't need to worry about the angular rotation of the block. Again, it doesn't rotate. But it does move up and down, so I need the linear acceleration. And I want to do that in terms of whatever coordinate is most natural. So here, the linear acceleration, well, that's a second derivative of position. And the position or displacement of this block is nicely described by x. So the acceleration of point B, or the block, is x double dot in the j direction. Now, if I look at the disk, well, the disk translates, right? So the mass center moves around, and it rotates. So for the disk, I'll need both linear and angular acceleration. Well, the linear acceleration of the mass center, that's going to be described naturally by this coordinate y. I mean, that's why we defined y in the first place, so that we could describe the displacement of g. Right? So that's going to be y double dot in the I direction. The angular acceleration, well, that was the first thing we defined, and that's going to be in terms of theta. right? So theta double dot in the k direction. Again, I don't know what x double dot is, and I don't know what y double dot and theta double dot are. But I know that the accelerations can be written in terms of those coordinates in this way. Now, we have 1, 2, 3, 4 coordinates that we've defined here. And it's a single degree of freedom system. So, in fact, we have constraint equations. If I tell you theta, you can find all of the rest of these. If I tell you x, you can find all of the rest of these. So we need to identify those constraint equations. And the constraints are naturally determined by looking at the velocities. So these constraints come from velocities. There's lots of different ways to develop constraint equations, but quite honestly, I find that this is, to me, the easiest one to apply and kind of to understand. Notice that the disk rolls without slip, right? So there's no slip at point C, which really means that the velocity of C is equal to 0. I mean, the velocity of the ground is equal to 0. There's no slip. So when I look at this disk, the contact point actually has 0 velocity. And you ask, well, how can that be since point G is moving around? Well, it's because as this thing rolls, there's a different contact at every displacement left and right. So as this thing rolls along, right, different points come in contact. But at the instant they're in contact, their velocity is actually equal to 0. So now, looking at some equations from, say, kinematics, your dynamics that you took, we know that the velocity of G is equal to the velocity of C plus the angular velocity of the disk cross the position of G with respect to C. Right? These are our planar kinematics equations that we learned in dynamics, 203 if you're at the University of Akron. Because G and C are both fixed in this object, this is how their velocities are related. But every single one of these I can write in terms of either a coordinate or something that I can measure. So here, what's the velocity of G? Well, in terms of these coordinates, velocity of G is equal to y dot in the I direction. What about the velocity of C? Well, that's going to be equal to 0. The angular velocity is theta dot in the k direction, right? Theta is the rotation, theta dot's the angular velocity. And then finally, the position of G with respect to C is going to be r in the j direction. So when I look at this cross product, k cross j is equal to minus I. So comparing the left and the right side, we see that y dot is equal to minus r theta dot. Okay, so now let's go and develop our second constraint equation. Now, this point B is described by x. Looking at this small pulley, we can actually derive this using similar kinematic equations. I'm not going to do that right now because it should be easy to see that whatever distance this block moves up, then this point on the cable moves to the right by the same distance. So looking at this small pulley, we see that x dot is equal to w dot. That's our constraint equation between x and w. How does that help us? Well, w is related to the velocity of A. So, in fact, the velocity of A is related to the velocity of B. They're different directions. A is moving left and right, B is moving up and down, but the magnitudes are going to be the same. So let's go and use our kinematic equation to relate the velocity of A in terms of, again, the velocity of this contact point. So the velocity of A is equal to the velocity of C plus the angular velocity cross the position of A with respect to C. Just like before, right? I'm going to express each one of these terms in terms of coordinates that we have identified previously. So the velocity of A is w dot in the I direction. Velocity of C, again, is 0. Theta dot k is the angular velocity of the disk. And now this vector is 3r in the j direction, right? Because going from C to G is 1r, and then the radius at this outer hub is twice r. So we end up with minus 3r theta dot in the I direction. So comparing the left and the right sides again, right, we see that w dot is equal to minus 3r theta dot. In fact, w dot was equal to x dot, right? So x dot is minus 3 times r times theta dot. And we can actually combine these, right? Minus r theta dot is equal to y dot. So this right-hand side ends up reducing to 3 times y dot. So every unit that the center of the disk moves, say to the right, this block moves up by 3 times that amount. And that's based on these constraint equations that we just developed. Now, it's important to note that these constraint equations are scalar equations. Clearly, the velocity of A is not the same as the velocity of B. B moves up and down, right? Again, A moves left and right, right? So I can't say that VA is equal to VB, but what I can say is that the magnitudes are identical, right? So I can say that x dot is equal to w dot. Again, when we look at these individual constraint equations, right, we base them on the velocities, but the constraint equations themselves are scalar quantities. They're just relationships between coordinates. Okay, what's next? Well, kinetics, right? Forces. We want to express the forces and moments in terms of the identified coordinates and directions, right? So, back in step 1, we talked about coordinates and directions. We want to use that to find and define the forces, just like we use them for the kinematics. All right, so really what we're talking about now is a free body diagram. I can't stress enough how important it is to draw a good free body diagram. For me, a good free body diagram includes all of the forces, and it defines those forces as vectors. So that when I go to apply momentum balance, all I really have to do is just take whatever I define these forces as and carry them over into the equations of motion. So again, we want to define the identified forces as vectors. And if we have a spring or damper, we want to make sure that we get that relationship right. So that those forces, and specifically those spring and damper forces, are consistent with the way that we're defining the coordinates. So notice that forces are either known, right? And a good example of those are the weights, right? So the weight of the block. Completely unknown, or at least unknown in magnitude. And that might be the friction force, Fr, right? Or T1, which was this tension. The last kind of force is also unknown, but related to the configuration. And that's like a spring force. So something that we can write in terms of the coordinates and directions. Again, force due to the spring is a great example. Right, so let's go and do those. Here I'm going to draw all of the known forces in orange. Right, so the weight here, minus mg in the j direction. That's known, right? The weight of the disk, minus mg in the j direction. That's also known. None of these other forces, though, can we write down now. Let's go and use green for the forces that are just straight up unknown. tensions, right? So this is, say, T1 in the j direction. Now this force, I don't know what it is, but I know that it's the opposite of this. So if this is T1j, this is now minus T1j. We'll say this is T2 in the I direction, which means that this is minus T2 in the I direction. Here we have the reaction force, which again, I can actually write in terms of components, Rx and Ry in the j direction. And finally, our last two totally unknown forces are the normal force, which I'll write as N in the j direction, and the friction force, which will be Fr in the I direction. Notice that this is a scalar, this was a vector. Finally, we have our spring and damper force. Now, recall that Y measured the displacement of the center of the disk, or the stretch in the spring. So if Y is positive, then the center of the disk moves to the right, which means that the force is then minus K times Y in the I direction. Likewise, if Y dot is positive, the damping force is minus B times Y dot in the I direction. And this is what I mean when I say the forces have to be consistent with any previously defined coordinates. So I got to make sure that however I define Y, then this is the correct description for those forces. So again, if Y is positive, then this force is in the minus I direction. If Y is negative, then this force is actually in the plus I direction. It would actually push the disk back to the right, but that's cool because minus K times a negative number gives me a positive number, right? So indeed, this force is pushing to the right. So before I go on, I do want to talk about this massless pulley real quick. Right, so here again, we just have a force R, the reaction force. This was minus T1 in the j direction. This is force T2 in the I direction. Because the pulley is massless, then the mass times acceleration has to vanish, right? I mean, m is equal to 0. So that means that the sum of the forces equals 0. More importantly, for our purposes right now, the sum of the moments also equals 0. This reduces to a statics problem. Not that the pulley's not rotating. It is, but because its mass is 0, its rotational inertia is 0, which makes the right-hand side equal 0. So now, looking at angular momentum balance about 0.0, center of this pulley, and let's assume that the pulley has radius s. Doesn't really matter what s is in this case. Sum of the moments has to be equal to 0, right? So the moment from this force on the right is s times T1 in the k direction. The moment from the force acting at the top is actually minus s times T2 in the k direction, which of course has to be equal to 0. I'll remind you that moments are defined as R cross F, right? So if you want to work the cross product out, totally fine. Well, looking at this, we see that S times T1 minus T2 in the k direction has to be equal to 0. So the only way that happens is if T1 is equal to T2. So in fact, the tension across this massless pulley is constant. Now, if this pulley had mass, though, then this right-hand side would not be equal to 0, and so T1 would not be equal to T2, right? It would be related to the angular acceleration of the pulley itself. So we can't always make this assumption. We only do this when we have massless objects. So here, I'm just going to combine these. I'm just going to call this quantity T, just to indicate and emphasize that the tension acting on the block is the same as the tension acting on the top of the disk. All right, well, we've got the forces. What's next? Well, the only thing left to do is formulate the equations of motion. So we want to apply momentum balance. Linear momentum balance and angular momentum balance on all of the objects. We already did the pulley, right? So we're not going to consider that anymore. Instead, we'll just focus on the disk over here on the right, and the block. And notice that what used to be T1 is now just T in the J direction. What used to be T2 is just now minus T in the I direction, right, corresponding to that force. Well, apply momentum balance. So on the block, again, the block doesn't rotate, right? It only translates. So we'll apply linear momentum balance. Sum of the forces equals mass times the acceleration of B. Well, we're just going to copy over a bunch of stuff that we've already done. That's kind of the nice thing about this framework is when I get to this stage, all I'm doing is just using stuff that I've already done. The forces, T in the J direction, plus minus mg in the J direction. What's the acceleration? Well, we define x as the displacement, x double dot in the J direction was the acceleration. If you want to pause the video, you can actually go back and find that on the previous slide. So this reduces to m times x double dot in the J direction. So looking at this, right, we only have stuff in the J direction. So taking that scalar component, we see that T minus mg is equal to mx double dot. And again, the disk doesn't rotate, so angular momentum balance would be trivial, right? If we tried to apply this, there are no moments produced, right? So the left-hand side 0, there's no angular acceleration, the right-hand side's equal to 0. We get 0 equals 0. Totally true, but not really useful. What about the disk? Well, because the disk can rotate and translate, we need both linear and angular momentum balance. So linear momentum balance is sum of the forces, mass times acceleration of the mass center. Well, copy these forces over. Right? So I have minus T in the I direction. Let's do the weight next, minus mg in the J direction. We'll throw the force due to the spring and damper, ky and by dot in the I direction. Friction force, that's there. And finally, the normal force. We got to be really careful that we don't forget anything, right? That's, I mean, part of the reason for doing all this is so that we don't forget stuff, right? This friction force, it's acting on the disk, right? So even though it's rolling without slip, we still have to add this and include this into the equations of motion, right? And then this equals the mass times the acceleration. Well, we used y for that coordinate, so that's my double dot in the I direction. Notice that I've got stuff in the I direction and stuff in the J direction here, right? So we need to split that up. In the I direction, we have minus T, and then we have minus K, Y, and B, Y dot. And finally, we have the friction force. In the J direction, I've got the normal force, and I've got the weight, J. And this is going to be equal to my double dot, again, in the I direction. And in fact, the J component here is 0. So taking the component in the I direction, we see that minus T minus K times Y plus B Y dot plus the friction force is equal to my double dot. And then taking the component in the J direction, N minus mg is equal to 0. Remember when I said that the normal load is the weight, but I didn't want to assume that at the beginning? Well, here's why. Because it works out, right? I can solve this for the normal load and find that it's actually equal to the weight. But I didn't have to make that assumption, and that's the important thing. So now let's go and look at angular momentum balance. I have a couple of different options for that. I can take angular momentum balance about the center of the disk. If I do that, right, I would eliminate the weight. I'd eliminate this spring and damper force. But I would also include moments from friction as well as this tension. Well, this is something that I definitely want to include. The other option I have is taking moments about the contact point, right? So this was point C. Because it's rolling without slip, we can apply angular momentum balance about that point. And the advantage here is that it eliminates this friction force directly. It also eliminates the normal and the weight as well, just leaving the force due to the spring and damper and the force due to the, or I should say the moment due to the spring and damper and the moment due to the tension. So let's do that. Sum of the moments about point C is the moment of inertia about point C times the angular acceleration of the disk. Well, let's go and calculate these moments. Again, moments are R cross F. So let's look at the tension first. R here, let's go from C to A. So that becomes 3R in the J direction. And then the force is minus T in the I direction. Right? So this is the moment produced by the tension about C. Let's do the spring and damper force next. Here, the moment arm is basically R in the J direction, right? Because we're going to go from C to G, and then cross the force itself, minus Ky By dot in the I direction. And that gives me the moment from the spring and damping force. That's got to be equal to the moment of inertia about C. Well, this disk, and again, this outer hub is massless, so really we just have this disk. The moment of inertia about the contact point is 3 mr squared over 2 times the angular acceleration, which is theta double dot, in the k direction. So now all I have to do is evaluate these moments. J cross I is minus k, right? I've got another minus sign there. So we end up with 3R times T, the tension, in the k direction. I'll put the k at the end. J cross I, again, minus k. So plus R times ky and by dot. Both of these are in the k direction. Equals 3mr squared over 2 times theta double dot in the k direction. So look what I have here. I've got 4 equations. I've got this one. I've got this one. I've got the component in the j direction. And then finally, I've got this, which I will take the component in the k direction, right, which essentially just gives me this left-hand side equals the right-hand side. And these are my 4 equations from momentum balance. Right, so what's next? Well, now we want to reduce this and solve. Here they are again. Right, this was on the block, this was on the disk, and then in light gray, I have what came from linear momentum balance on the disk. And finally, I have my constraint equations. Right, those are important. I can't forget those. So these light gray equations, essentially, they kind of decouple, right? Because notice that the friction force is unknown. So I could solve for the friction force as Fr. It's going to be my double dot plus T plus Ky and by dot. I could do the same for the normal force. N is equal to mg. In general, if you have a bunch of equations, right, you pick one variable, you solve for that, and then you substitute that into the remainder of the equations. Right? I mean, that's how we solve algebraic equations. Well, essentially, okay, let's solve for the friction force, which we just did, and then substitute it in. But notice it doesn't appear anywhere else, right? So essentially, I don't have to worry about this. Same for the normal load, right? N doesn't appear in any of the other equations. So the fact that they don't appear in those other equations means that really I only have to worry about 1, 2 equations up here, and then these 2 constraint equations. In fact, if you think about it, these 2 equations both came from sum of the forces equals mass times acceleration. I don't even have to apply linear momentum balance. I mean, it's still there, it's still valid. But I could get the equations that I need to solve by just looking at linear momentum balance on the block and angular momentum balance about the contact point on the disk. If I had taken angular momentum balance about the center of mass, well, that would introduce FR, the friction force, right? So then I would have to consider this. So now let's go and just sort of look at what's left. Well, solution procedure, solve for one of these, substitute in. Let's solve for t first, right? T here is equal to mx double dot plus mg, right? Just by looking at this equation. And so I'll take that and I will introduce that into this second equation. So I have 3 times r. I'll write that in red, right? Because I'm going to substitute the t in for this value, x double dot plus mg. And then I still have everything else. ky by dot equals 3mr squared over 2 theta double dot. So I'm actually going to go ahead and do a little combining here. I'm going to put all the acceleration terms together, and then I'll kind of put everything else together. Before I do that, though, I am going to factor out an r from every single one of these terms. So now, combining the acceleration terms, I get 3m here times x double dot, and then I get this term, minus 3m r over 2 theta double dot. I have the damping next, right? So that's going to be b times y dot. I've got this stiffness term, k times y, and then the weight, 3mg, I'll put on the right-hand side. So I get minus 3mg. Now, I can actually use my constraint equations to write this in terms of x. Remember the problem statement. I wanted to write the equations of motion in terms of the motion of the block. So here we need to eliminate theta double dot. Well, looking at this term, we see that theta double dot is minus x double dot divided by 3r. So let's take this and substitute it in. Right, so I have 3m x double dot, and then when I take this and introduce it into this term, I end up with m over 2 x double dot. For my y dot term, well, that I get right here. That's x dot divided by 3. And the stiffness term, well, because these are measured from a common configuration, we can just integrate with respect to time, right? And x we see is equal to 3 times y. So y is x divided by 3 equals minus 3mg. Finally, let's go ahead and write this kind of in our standard form. Right? So 3m plus m over 2, 7m over 2 times x double dot, and then b over 3 times x dot, k over 3 times x equals minus 3mg. And this is the equation of motion. Now, not a necessarily quick procedure, right? But this is a fairly complicated problem. But hopefully, if you go back and look, everything that we've done here is relatively straightforward, right? And that's kind of the goal. The goal is not necessarily to make this immediate. The goal is to make it straightforward so that I feel like I can solve for any problem that comes my way. Well, let's do a little bit more, right? Here's the equation again, right, in terms of x. Here's the system. Notice that I can identify the equivalent parameters, right? So the equivalent mass here is 7m over 2. The equivalent damping is b divided by 3. And the equivalent stiffness is k over 3. So given these values, I can calculate the natural frequency and damping ratio. Those we know are important response parameters. The natural frequency is the equivalent stiffness divided by the equivalent mass. So when you do this, you take k over 3 and divide it by 7m over 2. What you end up with is 2k divided by 21 times m. Right? Only the slightest bit of algebra. Pause the video if you need to work through this. And then the damping ratio, well, that's B equivalent divided by 2 times the square root of K equivalent and M equivalent. Again, I'm going to do the algebra for you, and what you get is B divided by square root 42 km. Pause the video if you need to work through this algebra. Right? And I think that's a good idea. In general, I think it's a good idea to periodically or even frequently pause these video lectures and go and make sure that you understand exactly what's going on. So here we have our equation of motion. We've identified the natural frequency and damping ratio. Not going to do it here in this lecture, but the response of the system is determined by solving this with the appropriate initial conditions. Right, so again, we just have our second order constant coefficient differential equation, single degree of freedom system, and we can go and solve that. So once we solve it, right, which again I'm not going to do in this lecture, right, but once we solve for x, we can go back and find a lot of stuff. Because all of these quantities, all the unknowns in our modeling procedure were written or can be written in terms of x. In particular, theta of t we saw was minus x of t divided by 3r. We saw that y of t was equal to x of t divided by 3. So once you know x, you can go back and solve for theta and y. I could figure out what the rotation is, right? I could figure out what the motion of the center of this disk is. But we can also do other things. Remember we had this friction force that was written in terms of y and t. Well, t we could solve for in terms of x. Again, once we know what x is. And we can do the same for the friction force. This friction force was m times y double dot. The next term was t, but of course t was mx double dot plus mg. Right? I say of course because I went back and I looked and I have it in my notes. And then k times y and b times y dot. So we can write this solely as a function of x. We'll use y double dot as x double dot over 3. And then we can also combine that with this x double dot term. Right? So we'd actually have 4m over 3 x double dot. We'd have damping terms that look like b over 3 times x dot. I'd have a stiffness term that looks like k over 3 times x. And then finally I'd have this mg piece. So if you know x of t, right, you can actually find the friction force. Again, knowing x of t means that you solved this equation, right? And that's for another lecture. But that's a lecture we've already done. So let's make the assumption that you can do that. Interestingly enough, we can actually combine this with the equation of motion. Notice that I have b over 3 x dot, I have a k over 3x. I also have those here. So, for example, solving for that term, right, and then putting it in here, and this is just a little bit extra algebra, we can write this as minus mx double dot minus 2mg. It's just algebra, right? Pause the video if you want to work through that. But the point is, the important thing is that once I know the response, I can go back and figure out a lot of these variables. I can figure out the tension, I can figure out the friction force. Finally, a little bit more, we could determine the static displacement. So the static displacement is the solution to the differential equations that doesn't change in time. right? So basically x of t would be some constant value, delta. I'll just use delta as the abbreviation for the static displacement. But I got to solve for delta. Okay, delta doesn't change. It has to solve the equation of motion, so this term would go away. Again, delta's constant, acceleration's constant, and it amounts to solving what's left. K over 3 times delta is equal to minus 3 mg, or delta is actually 9 mg divided by k, minus. So what we find is that this block actually falls down by this value. Notice it's 9 times what it would be if we just attached the spring to this block, right? And that has to do a lot with the kinematics of the disk and the system as a whole. So really, we have modeled this very complicated system in a very logical and organized way. Last couple of things that I will throw out here are just a recap. So in these last 2 slides, I took everything that I had done before in terms of the framework and the questions, and I've just given them to you on 2 slides. All right, I'm not going to read this off to you because we've already seen all of this, but this can be a nice reference for you as you're solving problems. Identify the objects, forces, and motion. These are really the things we want to think about. Coordinates and directions, this step, here's what we think about. Kinematics, that's what I do next, right? Here's what I think about. Define the motion in terms of these coordinates and directions that I defined in the previous step. Kinetics, free body diagram. And then finally, apply the equations of motion. And what I promise you is that this framework provides a general strategy to modeling any problem that we'll see in this class. If you can get in the habit of doing this, right, you'll be able to solve all of the problems. And you'll be able to model any problem that you see in this class, or more importantly, any class that you see after this. So that's it for this lecture. The last thing I'll throw out is that if you can internalize this and get comfortable and use this, it seems like it'll be just a super long procedure. It goes much quicker. I really tried to explain everything in great detail. To work through this doesn't take a lot of time, and more importantly, you don't get stuck anywhere. You don't spend an hour going, what do I do next, right? Because we have this nice framework where you've built up the things that you know are the things that you need in order to do the things that are next. So in the long run, this can save you time. So that's it for today. Probably a lengthy lecture, but I would argue that this is maybe the most important lecture that we'll have in this class, right? Because it really gives you a strategy and a framework for solving the problems, or at least the modeling problems that we'll do. So that's it. Again, I'm Dane Quinn at the University of Akron. Thanks for your attention. If you made it through this far, I'm always looking for feedback. Please leave comments either through the class website. You can email me, or you can leave a comment on the video. Take care. Have a great day. Bye. Well,